passionate like you, I'm let's just get the semester over with. Um, well, we're only going to, including today, we're only going to meet as a class 3 more times. So we have, next week. Um, and I think by then I will have covered everything I need to cover, even the new stuff. We'll see if it goes. I only have a small amount of notes that I have to get through today. And then, okay, but we'll see if, so, well, I guess the interest of not uh, fragmenting things. Does anyone have any homework questions? Oh, okay. Well, that makes things easier. Okay. Um, all right. So, all right. So, one thing that's very important is for the um, oral final exam part of the course. Um, I am going to put something in the notes that I'm going to post later today. So I'm not gonna like actually cover it here, but it'll be in the notes about some guidelines for that part. Like what sorts of things I'm going to ask about from different chapters in the notes. I guess a few sample questions, not an exhaustive list, but just to give you an idea. Um, like I'm not going to have you go to the board and write MATLAB code. So, um, okay. Um, and uh, so, so you can schedule it either during the last week of classes after Thanksgiving break, or during the following week, which is finals week. Um, and I guess like talking like 45 minutes to an hour at most time span. Um, and and also it should be in person, like I know that everyone here could do that. Like to like for instance, if I want to have you do something in the board. So, okay. Um, so alrighty. Um, also, um, I need everything in by Thursday. Okay. All right, so today is the 10th, so 17, 24. Thursday, December 8th. Um, because I have to have grades in by the following Monday. And actually want to be able time to look at your stuff. So until it's like, looks like a B. Sorry, A. Okay. So now, so what I covered last time, run kind of methods, were more broadly one-step methods for time-dependent PDEs, or really systems of ODEs that come from PDEs. All right. Um, so if you're trying to compute the solution at time tn plus 1, one-step method uses information that's available only in an interval from tn plus 1. Whereas multi-step methods, what I'll talk about today, use information from further back in time. Okay. Now, um, so the information about the solution prior to Tn. Yeah. Yn plus 1. Okay. Now, the general form of a multi-step method is this for an S-step method. So multi-step methods have a prescribed number of steps that's greater than one. You can have a two-step, three-step, four-step, whatever. So S is the number of steps. Okay. So on the left side, we have a summation as a linear combination of y values. And then on the right side, we have delta t times summation. That's a linear combination of f values. So when I have f, this plain old f with a superscript, that is a shorthand. So Fn is shorthand for f of Tn Yn. Okay. So all multi-step methods have this form. Okay. Now, the method is explicit if and only if the first of these beta coefficients, beta 0, is equal to 0. And the reason why is the output of this multi-step method is yn plus s. That's what you're actually trying to compute in terms of y values from earlier times. So if beta 0, oh, wait a minute. Sorry, not beta 0, beta s. Okay. Because if beta s is non-zero, we would have fn plus s, which would include yn plus s, the very thing we're trying to compute. Yeah. So once we just got caught up in this, different textbooks describe multi-step methods very differently. My own book describes multi-step methods differently, which is why I've written beta 0, because using the conventions in my book, that's when it's explicit. But I'm using this to conform to the MIT notes and certain other books. But it's something to be aware if you're looking at more than one source, what indexing do they use for multi-step methods? And apparently I had to be more careful about that too. Yeah. Okay. Now, okay. Now, so before I talk about specific examples of multi-step methods, I want to explain why people like to use them. Because even though we have a bunch of evaluations of f over here, remember 4-4 Runge-Kutta? That's a 4-stage method for 4-4 accuracy, and it had to evaluate f 4 times. Here too, we have s plus 1 total evaluations of f. But there's one big difference between a multi-step method and Runge-Kutta methods. So the pro of multi-step methods is there is only one new evaluation. Yes, of f per time step. So it is much more efficient than one-step methods that have a similar order of accuracy. Because even though you have all these f values being used, all the other ones were evaluated during prior time steps. There's a lot of information reuse. So that's very good. what's a con? Because if you have a multi-step method that is using method y values from earlier in time, what are you going to do when you're just starting?
If you start with an error, it's going to amplify. If you make an error early on, it's going to.
Well, all time step methods have that issue. That's why it's important for them to maintain stability. But like, okay, so suppose your method depends on where you are at the current time and say 2 values prior. Well, when you're at time t0,
there was no time.
You have no information from before. So you must compute, in that case, yes, must compute actually s minus 1 starting values.
So this only would be s value and s minus 1 value.
Okay. I'm sorry, what?
So we need s and s minus 1 value.
Yes, right. Okay, so, well, wait. Okay, the number of values you need at any point are actually s. It's just that when you're starting out, you have 1, that's your initial data. You need s minus 1 more to have a total of s to compute your next value. So you still have to use a one-step method or something nature to get the ball rolling, and then you can reap the benefits of a greater efficiency of multi-step methods. Okay. Also, we have to be careful about not just any one-step method. It has to be at least the same order of accuracy, or better. That's fine too. But so if you want to use like a fourth order multi-step method, you can't be generating your starting values using Euler's method, because that first order accuracy, those starting values will taint the entire solution. So you need to make sure you're working with a consistent order of accuracy for your starting values and your multi-step values. So a multi-step method cannot be used by itself. I should mention that one of my students works on multi-step methods. That's Bailey Ruster. She created a multi-step version of my own time-stepping methods for PDEs, real subspace spectral or KSS methods, and those have always been one step. So now we have a multi-step version, and really is to get this benefit of less work per time step. Okay, so any questions about the general setup? All right. Okay, so now I can talk about the different categories of multi-step methods, some examples. Okay. The categories of multi-step methods. First, we have what are called Adams Bashforth methods. Okay, now Adams Bashforth methods, they are all explicit. And we have, and they all have the property that, so alpha s is equal to 1. Alpha s minus 1 is equal to minus 1. And alpha 0 up to alpha s minus 2, so all other alphas are equal to 0. Okay. And because they're explicit, beta s must also be 0. Okay. So the left side of an Adams-Bashforth method is actually quite simple. So, and the order of accuracy is S. So the error is order delta t to the S. Okay. So, so they all have this form. Y n plus S is equal to Y n plus S minus 1 plus delta t, sum of 1 to S of beta j f n plus j. Oh, wait, no, 0 up to S minus 1. Okay, yeah. All right. And in this case, I can actually give you a formula. So since the alphas are all specified, it's only the betas that we need to determine. And the formula for the betas is integral from 0 to 1 of, make sure I get this right, a Lagrange polynomial of degree s minus 1. Okay, so these are Lagrange polynomials for the integers from 0 up to s minus 1. So these Lagrange polynomials are equal to 0 at all of these points, except for one of them at which are equal to 1. And the reason why those are betas is based on this equation that's actually satisfied by the exact solution. But if you integrate both sides of your ODE, y prime is equal to f. Okay. So the exact solution satisfies, so this is like the integral form of the ODE. So the betas they play the role of quadrature weights. Because when you are approximating an integral by fitting your integrand with a polynomial, the quadrature weights are the integrals of Lagrange polynomials. So that's what we're using here. Okay. But I mean, you can look up coefficients for Adams-Bashforth methods on whatever site and get them for many different orders of accuracy. So as an example, the two-step Adams-Bashforth method is this one. Yn plus 2 is equal to Yn plus 1 plus delta t. And we have 3/2 Fn plus 1 minus 1/2 Fn. Okay, yeah. So our computing solution at this time this is the time we're at currently, and we go back one step further to use this value. Okay. So we end up with beta 0 is 3/2. No. Beta 0 is -1/2, and beta 1 is 3/2. Generally, the sum of betas equal to 1. The sum of the alphas is 0. Now, it sounds like Adams-Bashforth methods were a collaboration between Adams and Bashforth, but actually they were not. They were invented entirely by Adams, but he was working with Bashforth. So Bashforth was not a mathematician, I guess, to contribute to the problems from whatever other discipline they're working on and needing ODEs to solve. So I guess whatever ODEs it needed a method to solve for. So then Adams came up with this to solve. So, so even though Bashforth was very much a contributing scientist, I guess he was riding Adams' coattails as a mathematician.
It'll be fun to know.
Yep. It's kind of weird how things get named. Well, it's like, okay, so my own methods, pre-low space spectral methods, like that term does not appear. I developed them for my dissertation, but that term does not appear anywhere in dissertation. I hadn't decided what I wanted to name the methods yet. When I was having to publish a paper, I was like, well, I really need to come up with a name, and I made sure that no one else was using that same term, and just a little Googling, and I use it. But lately, my colleague at Naval Research Lab, Peter Jordan, was recommending that I reconsider the name, that I should come up with a name for these methods that has my name in it.
Yeah.
And like, but I feel too self-conscious to name a method after myself. I would never do that. In fact, one of the many algorithms that my advisor, Gene Gallo, came up with many algorithms during his career, and he never named them after himself. And there was one that, it was a modification of Lanchos iteration that plays a role in conjugate gradient. And he and Professor at Berkeley, Bill Kahan, came up with a modification of that. But basically calling it Lanchos by diagonalization, even though Lanchos was long dead and had no part in it. And once Gene passed away, his friend and former student, Michael Saunders, started a campaign to have the method of a name of a method changed to Gallo-Kahan diagonalization. And so he even corrected me in my own talk, because I called it by the old name. He said, no, we're calling it this now. It's like, okay. And so within a couple of years or so, the new name stuck. So even though I'm not gonna, the idea is if my colleague, Dr. Jordan, if he does a paper himself that I'm not involved in, where he cites my work and refers to it by a proposed new name, that way I'm not naming a method after myself. He's naming it after me. And the fact that we consult with each other is swept under the rug. Trouble is I can't think of what the new name should be. Well, the thing is, like with Bailey's work, I want to call. I really do want to call it an Adams-Brester method. I'm not sure if she's on board with that, but yeah. But I think it would be very fitting. So, yeah. Well, I'm gonna take Gauss elimination. Gauss did not invent Gauss elimination, but okay. Are there any questions about this Adams-Bashforth? Okay. All right. Now, the other kind of Adams method Adams Moulton. Also invented entirely by Adams. But, and these are implicit. So beta S is non-zero. The alphas are the same. So then here, the summation would go from 0 up to S. The formula for the betas is the same, except the degree would be S. Because with the extra term in here, you have one, your interpolation polynomial is 1 degree higher. And you're interpolating 0, 1, 2 up to S. And the order of accuracy, therefore, because that extra term is delta t be S plus 1. Okay, this part is exactly the same. So some of the betas would still be 1. Okay. All right, so actually a two-step Adams-Moulton method is 2, 1 plus delta t. So we have okay, 5/12 Fn plus 2 plus 8/12 Fn plus 1 minus 1/12 Fn. I know I could have written the 8/12 as 2/3, but here it's easier to see that the betas once again are summed to 1. So because we have yn plus 2 here and fn plus 2 here, that relies on yn plus 2, that's what makes it implicit. So we need an iteration to solve it. So even though, for previous Adams method, I wrote those two-step, also used values as far back as fn to get yn plus 2. So the amount of information used is the same, it's just used differently. And because that leads to an extra term in here, that's why we get third order accurate for this method as opposed to second order accurate for the previous one.
Is it two-step?
What?
Is that two-step?
There's a two, yeah. So this also is a two-step method. Oh, okay. Yeah, I've had a problem with students telling like 2 is far from a z. That's why for a z, I've trained myself to put the little dash there. Yeah. That's why also for the partial derivative symbol, I make it very curly. So that can be confused with 2. Yeah. All right. Now, the next type of multistep method is not really a new type. It's actually a combination of the two that I've shown you. So Adams-Moulton predictor corrector. Okay. And this is where Bolton comes into the picture. Adams invented both explicit and implicit multi-step methods, but Moulton was the one who realized that the two could be used together in a very efficient way. So the idea is, here's a procedure. And the way to remember it is PECE. So the first step is predict, evaluate, correct, and evaluate again. So PECE. Now, what is actually done during these 4 steps? But for the predict part, you just use an Adams batch 4 method. So yn plus, I'm going to call it p instead of s. Because the two methods, I'm going to use 2 methods, an implicit one and an explicit one. And they don't have to be same number of steps. Okay, so this is the same as batch form method, but with P step instead of S step. But I'm going to call the output y tilde n plus p. I just realized this is going to complicate matters when it comes to, like I said, there are different ways of describing multi-step methods. And I didn't really think it really mattered which convention one used. But when it comes to predictor corrector methods, it's not a good one. But I got to make it work anyway, somehow. All right. So this is, you can think of this like as an initial guess to the solution at the new time. Okay. Then what you do is you substitute this into f. So f n plus p is equal to f at tn plus p y tilde n plus p. I'm not really liking how this notation is shaking out. I may have to rethink how I label things. Okay. So all right. For a correction procedure, for this we're using an implicit Adams method, so an Adams-Moulton method, to perform a correction. So that would be y n plus c is equal to y n plus c minus 1 plus delta t. And for this, you're going to have c minus 1, beta j, f n plus j. But then for the final term in this, you're going to use beta c f tilde n plus c. Okay. So you're using an implicit method much like an explicit method. There's no iteration. You don't need to solve an equation like you normally would for an implicit method. You're taking a value that you computed earlier. Sorry, it should be a tilde. Okay. So this value you can compute during your evaluation step, you use down here. So you know, from using the structure of an implicit method, it's still very much plug and chug as if it's an explicit method. And now you have your solution at your new time. That is your final value. But you still need the F value to go with it. So you do a force valuation to set the stage for the next time step. Like I said, the number of steps in your predictor and the number of steps in your corrector do not have to be the same. So if they're not the same, that means that these indices will be different, but I'm sweeping that problem under the rug. The point is, you have this tilde value somewhere, go use it. All right. So you're able to get the benefits, like a higher order accuracy of an implicit method, but the amount of work involved is closer to that of an explicit method. Now you're evaluating F twice per time step, but that's still not bad. The order of accuracy, those order delta T to the minimum of C plus 1 and P plus 1. So the order of accuracy of your predictor and corrector both impact the order of accuracy of the overall scheme. So that's why it's a good idea to have the number of steps in your predictor and corrector be the same. So that way you're not like wasting order of accuracy. But again, it's not a requirement. Now, what you could do is, after you get this far, you could use this value over here as an iterative procedure, like fixed point iteration. So that's really more like an implicit method, where the explicit method gives you an initial guess. But the typical predictor corrector framework is just predict, evaluate, do this once, and you say, okay, this value is good enough, and then we move on. Okay. Right. So, questions about this approach? Well, it's a very long time ago, like I think the early 1900s, or was it the late 1800s? Super long time ago. Yeah, and it's kind of weird how these are methods that these days people code up in MATLAB, and there were no computers back then.
That's what I've been thinking.
So
Sit down and do each thing, and then it takes a decade to just get one verification.
yeah, like okay.
Yeah, we barely had electricity back then.
Yeah.
Getting enrolled was just
Okay,
because you have to do it multiple times to verify that it holds.
Okay, 1883 was when the paper was published by Adams and Bashforth. Okay.
It was invented in 1891.
Yeah. So there's a paper by that's when Edison.
No, Nikolai Tesla.
Oh, okay.
I was like, this is 1883.
I wonder what Tesla would think of Musk, but
Think this what?
of Elon Musk.
Nothing. He'd be too busy.
Yeah. Okay. So the paper put out in 1883 by Bashforth says that the title of the paper is "An Attempt to Test the Theories of Capillary Action by Comparing a Theoretical and Measured Forms of Drops of Fluid, with an explanation of a method of integration employed in constructing the tables which give the theoretical forms of such drops, by John Couch Adams." So it might have actually taken less time to develop and analyze the method like to show that it has, this order of accuracy, but to actually use the method even once, like carrying out all the computations.
Yeah.
And now I'm thinking like about how even like as late as the 1940s or so, or when people had a job title of computer, they'd sit at a desk all day and solve systems of equations. So were these like the uh, quintessential evil advisors who would enlist their students to um, uh, um, grind out all these numbers? Um,
Probably they did it themselves. They just had fun doing it.
yeah. Well, let's see.
It's possible.
So Adams was, oh, and Adams didn't live much longer. He died in 1892. Okay. He was a British mathematician and astronomer. Um, okay, he was a professor in the University of Cambridge from 1859 until his death.
Oh, wow.
Okay. Oh, he has a crater on the moon named after him. Um, oh, that's weird. Uh, okay, something's on here. Oh, okay. Um, the crater on the moon named after him is jointly named after him and two other people, one of whom is Charles Hitchcock Adams. I can't tell if it's any relation, but Charles Hitchcock Adams is the father of Ansel Adams, famous photographer. So, okay.
Oh, yeah.
Hmm. Okay. Well, dang.
That's interesting.
Yeah. But yeah, like trying to do all that to do the equivalent of what we have MATLAB do today. Um,
It's like, I don't know.
yeah, like how many decimal places did they use?
And from what I know, paper was really expensive. They did not just available.
Yeah, and ink.
Ink.
Yeah.
They were constantly staying for days.
Wow. Let's see what's known about that. Like, I'm sure there's some information back in about how mathematicians functioned and yeah. But I guess that's also why unfortunately it was a province of the wealthy.
They actually really wanted to take history of math. But
Oh, right. Oh, right. We don't count it, sort of. Yeah.
it doesn't count, so.
Yeah.
And I don't have enough energy to take something for fun.
Okay. Um, okay. Are any questions about this? So one other category of multistep methods is very different from Adams. Backward differentiation formulas, or commonly known as BDF. Now, these are kind of opposite Adams methods. Like Adams methods, the coefficients involved are based on an integration rule, but here the coefficients are based on a differentiation rule. So we have 0, S, alpha J, Y, and plus F. And on the right side, there's always just one term. Beta, 0, let me make sure I have this right, yeah. 0, no, sorry, beta S, F, and plus S. So the idea is you're trying to solve y prime is equal to f. So f is all you have on the right side, and over here you're basically trying to approximate y prime. Okay, so alpha j over Okay, so V's are equal to Lagrange polynomials of degree S minus one evaluated at J prime. To get the numerical differentiation coefficients. Oh, and I'm wondering if I have it entirely right. Okay, because we're doing backward differentiation. Okay, I think that had to be minus J then. Okay. I may have my indexing off, but this is a general idea, I promise. It's not come up on homework anyway. All right. So, um, implicit or backward Euler is actually, it fits the form of a PDF. But a more interesting one is a two-step PDF is so 3 yn plus 2 minus 4 yn plus 1 plus yn equal to delta t f n plus 2. Oh, yeah, 2 here. And in general, an S-step PDF has order actually delta t to the s.
Stupid question, but it's a bit right. We're still always solving for y and plus 3.
Yeah, y n plus s.
And plus
Yeah, so these values we already have.
that we don't have.
Yeah, yeah. And because we have fn plus s on the right side, all BDF methods are implicit. Right. Now, for each value of s, you get a different method. But it turns out all of the viable BDF methods are known. The reason why is it's been proven. They are unstable for s greater than 6. So there are only 6 possible BDF methods of orders 1 through 6. The lowest order ones being implicit Euler. And it goes up from there. I'm looking up something in my book about multi-step. Okay. Oh, whoops. I was looking at something in a book about it, and I realized that the formula I have for the coefficients, the alphas, is wrong. I've been keeping track of mistakes in my book so that I can correct them for another edition. And I hope that this one I'd already made a note of, but of course I did not. Dang it. Okay. Okay. But that actually isn't what I want to look for. There's one other kind of multi-step method I want to show you, if I can find it. Ah, yeah, I found it. Okay. Uh, okay. So not all multi-step methods are necessarily atoms or BDF. So in my other category, just as an example, called Simpson's method, is related to Simpson's rule for numerical integration. So it's this is a two-step method. Y plus 2 to n plus t have 1/3 f. Okay. I just want to, yeah. N plus 2 plus 4/3 f plus 1 plus 1/3 f n. Okay. Now, what's weird here is that your beta coefficients, here they sum to 2 rather than 1. But the reason why is, look at these, they're 2 apart. 2 time steps apart, so that's why the beta sum to 2. Also, these weightings of these f values is just like what you see in Simpson's rule for integration. That for Simpson's rule, a basic Simpson's rule, you're evaluating integrand at the 2 endpoints and the midpoint. And the value at the midpoint gets 4 times the weight of the values at the endpoints. So that's where the method gets its name. Now, what's interesting about this is it is 2-step, but it is 4th order accurate. That may seem kind of surprising. Until you keep in mind that Simpson's rule for numerical integration is also 4th order accurate. So it seems wonderful that a method that is cheaper, being only 2-step, is so accurate. But there's a drawback to that. It is what is called weakly stable. I'll talk more about stability next week. But when a method is, so this method, due to its weak stability, can allow for solutions that have spurious oscillations that shouldn't be there. So it's not all good about this method, which is probably why people tend to use Adams methods or BDFs instead. In fact, MATLAB's stiff ODE solvers use BDFs. Okay. Questions about this miscellaneous categories? Actually, the only homework problems you have on time event problems are actually from what I'm going to cover next week on methods for a one-way wave equation. So you'll get all the information you need back. But at least you'll have a well-rounded knowledge of time-stepping methods, between 1-step and multi-step. Okay. All right. Well, I guess that's it for today. That's it for today. So it's already checked you guys don't have homework questions. So.